In this video, we're going to cover section 1.5.2 on first-order reactions. Let's consider the following elementary reaction step, where the reactant A decays, resulting in the formation of product P. If the reaction is first order with respect to the concentration of A, the corresponding rate law expression is as follows. The overall rate will be equal to the rate constant K1 multiplied by the concentration of A. Now, like we saw for zeroth order reactions, the reaction can also be written in terms of the time derivative of A. And in doing so, we can equate this expression for the consumption of A with time to our rate law expression, K1 times the concentration of A. And so we end up with the following. As a result, this differential rate expression relates the time derivative of A to the rate constant and the reactant concentration. This is also a standard differential equation that can be integrated as follows. So if we take that differential equation, we multiply both sides by dt, so we end up with K1 dt on the right-hand side. And if we divide both sides by the concentration of A, we end up with dA over A on the left-hand side. Now, if we integrate both sides with respect to the same limits we saw for the zeroth order reaction, we have A naught to the concentration of A at some time t, and t equals 0 to some time t. Now, this takes on the form of the integral dx over x, and the solution to that is ln x. And so if we solve both sides of this expression, we end up with ln A minus ln A naught equal to negative K1t. So the integrated rate law for a first order reaction, we can take that rate law and rearrange it in a couple of ways. We can group the concentrations such that we have the ln of A over A naught equal to minus K1t. And we can also show this in an exponential form, where if we take the anti-logarithm and then multiply both sides by A naught, we end up with the concentration of A being equal to A naught e to the minus K1t. So for a first order reaction, the concentration of A will undergo an exponential decay with time. And this is quite different than what we observed for zeroth order reactions, where we saw a linear dependence or a linear decay with time. And in the following figure, we see two exponential decays. The only difference between these are the magnitude of their respective rate constants, where K large is 3 times larger magnitude than the rate constant K small. And so you can see that the decay of K large is going to occur much more quickly and approach that zero concentration faster than a rate constant with a lower magnitude. Now, for a first order reaction, a good linear fit to the experimental data will be observed for a plot of the ln of the concentration of A against time if there is a strong association between these two variables. The slope of the linear fit corresponds to minus K1, and the y-intercept corresponds to the ln of the initial concentration of A. Again, it is important to note that the comparison of experimental data to an integrated rate law expression requires that the variation in concentration with time be accurately known over a wide range of reaction times to determine if the reaction indeed follows a certain order of dependence. And again, this just highlights that it's important to monitor the reaction for a sufficient amount of time such that you observe generally 2 to 3, 2 to 4 half-lives for that particular reaction. This is just to ensure that the order of dependence, the model that you're using to fit the data, is an accurate model and one that best represents that particular elementary step or reaction mechanism. Now, if only the reactant is present at t equals 0, the sum of the reactant and product concentrations at any time must be equal to A naught. Using this idea, the concentration of product with time for a first order reaction can be determined. And so this is very similar analysis that we just showed you in the previous video for zeroth order reactions, where we can equate the initial concentration of A to the sum of the product and the concentration of A at any point in time. Rearranging this expression, we end up with the product concentration equal to A naught minus A, and then we can carry out our substitution, where the exponential form for our first order integrated rate law, A is equal to A naught e to the minus K1t. And so we can equate the product concentration to the product of the initial concentration of A and in brackets 1 minus e to the minus K1t. So for a first order reaction, the concentration of the product with time is dependent on the initial concentration of the reactant. So similar to zeroth order reactions, we can calculate the half-life for a first order reaction. So the time it takes for the reactant concentration to decrease to 1/2 of its initial value is as shown. So if we start with the integrated rate law for a first order reaction, and we substitute for the concentration of A with 1/2 the initial concentration of A, then we can include the subscript 1/2 with our time. If we rearrange this expression, we end up with the following. T1/2 is equal to the ln of 2 divided by the rate constant K1. So unlike zeroth order reactions, for a first order reaction, the half-life is independent of the initial reactant concentration and only depends on the rate constant of the reaction. So if you have any questions about integrated rate law expressions for first order reactions or our discussion on the half-lives of first order reactions, by all means, send me an email. Thank you.